Okay. Okay. Today's date is the 24th of January 2026. The time now is the 2:11 a.m. Let's go to what's this? Oh, this music. No. Read. Let's go to read. So basically, I put the keyword read before it. Reader mode. We got 11 minutes. Basically, this is what I call a hard pointer. So it's basically a pointer that can never be deallocated. Soft pointer something can be deallocated. Hard pointer can never be deallocated. Part of it in NSIGII project. Okay, as a policy, let's make it in NSIGII, N for November, S for Sarah, I for Indigo, G for Golf, I for India, I for India. In NSIGII, in honor of SA, which is high to low tone. Low to high tone. SA, you say with a high tone, high to low. No, you say you say with the okay. Anyway, it's a low to high tone, so that's why I'm making the two I's at the end. So this is basically the Devil of the Two article I wrote, but it's called a symbolic interpretation to trinary logic. So three things we saw about. So I solved the problem. I solved the maybe problem. It's about the maybe problem, but treating like a pointer. A computer's final instant intent. But we're gonna cover some other things. We just have 9 more minutes, 9 minutes 54 seconds to address the pointer problem, which are soft and hard pointers, which is the goal of this. Before we move on to the other one, which is the spring echo physics. Okay. Read aloud. Let's keep around.
I solved the maybe problem by treating it like a pointer, and computers finally understood intent. How symbolic interpretation turned trinary logic into a memory allocation problem. Posted on January 19, 2026, #webdev, #polyglot, #programming, #openexus. I used to think maybe was just indecision, until I realized it's actually a pointer problem disguised as a logic problem. Here's the 7-minute story, and the symbolic interpretation engine that let me build systems where I love to hate you has 3 valid interpretations, and the computer knows which one you mean.
Okay, so this is a pointer problem. So this is gonna listen to code, so I pause it because of the code. But this is basically have 3 pointers to some data. It doesn't matter what program you use, C, C++, Rust. Just either pointer to nodes, the pointer data, what is like a data structure, data point like a node, so still person tree. The node is what you call it, point to the data structure. It can be a node using a linked list, a node being easy to allocate. It can be a node, like a graph node, allocated to a linked list, or any kind of node, like a linked list node, or like a point to a double linked list. It doesn't matter how you do it, the pointer problem is the problem of 3 pointers. There's 3 pointers included in the resolving of that state for human intelligence. So basically, the model on showing human things are preserved. So this is the problem the program here. The pointer problem noted about. Response equals, do you consent? Yes or no? If response equals yes, consent equals true. Else consent equals false. No equals maybe equals no. No, look at this angry guy. Maybe equals no. But maybe could mean yes. So insane. So this is the words of the first people. Okay, let's go. Continue with that. Let's continue from here.
I used to think maybe. Here's the 7 minutes. Traditional approach response equals input. Do you consent? Yn, if response equals y, consent equals true else. Consent equals false #, maybe equals no pouting face.
So it's basically that's the problem. The bug.
Enter full screen mode, exit full screen mode.
Oh no. So
The bug. There's no pointer to intent. Type. What kind of answer? Yes or no or maybe. Value. What did you say? Yes, maybe, IDK. Memory. What do you mean? Consent, refusal, thinking. When you say maybe, the computer needs to know. Do you need time? Allocate memory for future decision. Do you want more info? Allocate space for clarification. Are you refusing politely? Deallocate, reject request. This is a pointer problem. We need 3 addresses, type, value, memory, to resolve one word. The symbolic interpretation break.
So basically, the goal here is to have 3 pointers: type, value, and memory. But you cannot have a token type, value, and memory. But you have a token kind. Because this kind is basically clarification. So you have many types in one kind, and that kind of is like a heterogeneous kind or homogeneous kind, depending on how the heterogeneous. So you get how to structure. So you get homogeneity of a type, which is a kind or kind of woman. A woman is a type of woman. A girl is a type of for example, a girl is a type of woman. Is a kind of woman. A girl is a type of woman. Yeah. A girl is a type of woman. A young girl, a teenage girl is a kind of woman. A woman is a woman is a full is a woman is a type and kind of girl of teenager and a young teenager and a woman and a child. And then you get the adults, so you get the same for the males, but you get 2 women, so you get 2 women to 1 male, because of double the power, double the strength. So, heterogeneous. So this is a kind of like a heterogeneous kind is like a mixed kind of data. So heterogeneous, homogeneous. So I'm saying it works the same that way because it's really a type, value, and memory relationship that can resolve classifications of kind and type in that kind of relationship model. So don't try to limit yourself to thinking of type only. Think of a kind or token kind, the kind of data that is being allocated for via structured heterogeneous only, or structured or unstructured via heterogeneous only, unhomogeneous. This is all structured and classifiable. Yeah.
Breakthrough. I realized. I love to hate you isn't ambiguous, it's symbolically triple bound. #3 valid interpretations interpretation _1 equals. I enjoy our rivalry. #love, hate, you interpretation _2 equals. You frustrate me daily. #hate, love you interpretation _3 equals. I'm conflicted about us. #maybe a love, hate. Enter full screen mode, exit full screen mode. The computer needs 3 pointers. Token type. Is this love?
Or
Hate? Both? Token value. Which emotion is dominant? Token memory. What action should I take? This is exactly like the maybe state. Type. Trinary, yes, no, or maybe. Value. Current state. -1, 0, 1. Memory. Allocated space for resolution. The NSIGII pointer architecture. Instead of forcing binary, I built a symbolic pointer system. From data classes, import data class. From typing, import optional at data class.
So you go to symbolic position Python, but basically this is saying, so you got token type, token value, token memory, and you got the resolve, and you got the resolver. Each of token, so basically it's meant to allocate memory for some kind of system, you know. But you know, this one is very basic implementation. But the goal is to have something called like a dynamic program one. So it already has some space allocated for its own operation. So the program doesn't have to go through linear sequence of instructions to do the job. You have to go through. You just have to allocate space and say, oh yes, I have space. I can start my operation. I can continue. Can resume. So pointer is intended to three components. Token type to resolve, token type to give the echo chamber is a memory management. So you got the echo server, but you know the echo server is what we're going to this video. So the memory verifier is an ecosystem, like, you know, but you know that's a bit more complex. So you know it's basically meant to send memory message and allocate memory. But you know, usually, so if you've got an echo server, like a web server is echo, it relays information. But you know, the goal of echo service is to, you know, just for you to build a full server. But this is a single echo server, so it's a work in progress. So it's basically gonna send you what you need before you need it. So it's gonna send you what you need before you actually need it. So it's gonna work on your terms. So it's gonna work on, you know, if I send you something, you're working on it's gonna relay that thing, send that thing back. That's what ecosystems do. But they don't send it. They send it over the system of a secure channel. So you're gonna work using this kind of framework of echo chambers. You know, it's gonna bounce off the system because it's the server. It's gonna echo back some data, so something that's meaningful. So basically that's finished. You can go and look at this article. I'd love to hate you. To hear that forever, but you know, go and look at that yourself. So continue with the framework of organizers. What we do now. So this is basically unlike me. So we're gonna go here, we're gonna go back, and we're gonna go to here. Oh, I can use OBS. I have OBS and never using it. Oh my days. So you can go here. I can go to lights. You can go to one of this. I sold it, but Springfield linear, Springfield surface. So this is the actual one for full spring of force, but we're gonna use this one non-linear Springfield tutorial. So basically, this is the linear and non-linear Springfield tutorial. I've been dying to do, but you know, this is basically on sciencebodies.org. Science for project. So basically, this is science fair project. So you know, we got the force equals the kind of kinematic force plot of an axis case with the, you know, the force. So basically, you got the force of something acting on something, which is called kinematics. But you know, kinematics of a system. Okay, you got inverse kinematics, which is the inverse force happening on the system. But K stands for kinematics formula. So K is basically basically the change as a unit of state. So yeah, you get kind of formula. So let's look at this more formally. So this is a linear spring. So this is saying. So we're looking for non-linear springs. But we've got the linear spring equivalent if we do need it. So this is what we need. So we need to do the integration of it. So f of u, use a unit of du. D is a differentiation of u. Yeah. So let's start. So let's start reading this article on reader mode. So
Linear and non-linear springs tutorial. Reference materials.
So let's try here, definition.
Definitions. A linear spring is one with a linear relationship between force and displacement, meaning the force and displacement are directly proportional to each other. A graph showing force versus displacement for a linear spring will always be a straight line with a constant slope. A nonlinear spring has a nonlinear relationship between force and displacement. A graph showing force versus displacement for a nonlinear spring will be more complicated than a straight line with a changing slope. Equations at a glance. Swipe left to see more. Linear springs. Non-linear springs. force, stiffness,
So basically says, this basically comes to my formula, mate. So let me just go to put force, stiffness, and what?
stiffness, potential energy. Swipe left to see more. F, force in newtons, N. X, displacement from spring's neutral position in meters, M. K, spring stiffness in newtons per meter, Nm. P, potential energy in joules, J. U, is a dummy variable used for displacement in the integral for potential energy of a nonlinear spring, in meters, M.
Okay, so we've got definitions, but I'll say these definitions are not, it's not fully complete. So, I'm going to go through it myself now to show you what I mean. So, we got the linear system of linear spring, force equals K. K is the stiffness of a newtons per meter. The force they're going to put on the system. But K is the spring stiffness because IK, which is the inverse kinematics. So if you get a push, you got a pull. So if I'm pulling on this spring, it's pushing me double. It's pushing me double. So basically, if I'm pulling off any object that's no spring, this linear spring applies. But it is not complete in the non-linear system. So I'm going to redefine the definitions properly. So we got F, which is force in newtons. We got the three laws of force. Force equals mass acceleration. Net force equals 0, and force equals negative force. But these are all formulas of space physics, so they work on the kind of space of space. So I'll start to define the stiffness first. The stiffness is defined as K equals change in force over change in X, which is the K is the stiffness of K equals the differential of force over the differential of the X, which is N divided by force divided by M. So for this to be coherent in the system of linear equations, I'll change so K is equal to the change, the derivative of F. Yes, I agree with that decision. K is equal to over the derivative of X. But X is not X is a unit of a dimension, which is like based on a Soka Torah. So basically, of my lambda calculus. So you go like the Lapis calculus, which works in polar currents. You go to lambda, which works in power. So if I were to derive this, the power, which is lambda, which I don't know how to do yet, I will use the Lapis one, which is the backward state. So the stiffness is K, which is the stiffness. But you got K, you got IK. So IK is the inverse kinematics of K to the force over the system. So that the IK will be the derivative of the force over one over the derivative of the force one over the derivative of the force. Divided by the derivative of the K. So it takes one entire unit of the force, derivative of the force, one over the force, and one divided by derivative. So this is IK, the inverse kinematics, but this one is an entire unit of the system. So it is like having double the force pulled or 10. So if I have to do it properly, so the summation up to the should be so it would take so if I'm pulling on a force, I have a push. If I'm pulling on a spring per newtons, K is newtons per meters. There's a 10. So if the newtons is meters is 10 meters, the newtons is the force. The newtons let's say the force is 50 newtons. So 15 divided by 10 is I don't know. 15 divided by 10 is 0.5 newtons per meters. Yes, but that will be the change in the force K. So K would be IK would be 1 divided by 0.5 newtons per meter, 1/5, which basically the inverse kilometers of K would be 1 over 0.5 meters, but 0.5 newtons per meters would mean that there is the shear unit of meters. So they have to have 0.5 the shear unit for 5 meters for the meter. So the shear rate of meters, only shear working. So you have to then have the meters separate. That would be 0.5. The meters would be whatever. So this was 10 meters. So they share 10 meters. 10 meters would be for the new. So that would be so if the IK owns a tenth of it, a tenth of 50, which would be 5. 5 meters, the share a 5 meter ratio, so the share of 50, and but these first, because the inverse kilometers have to have so this share 5 meters of force, 5 newtons, 5 so if you get 50 newtons, this share 5 newtons. 5 newtons of force, 5 newtons, and this is basically a tenth. This here a tenth of 50, which is 5 newtons, and this 5 newtons will be the same for every meter it takes. So the meter will be a tenth of the meters. So a tenth of the meter will be divided by 10 will be 1. So we should 15 newtons divided by meters. So this here the meters, the newtons, which is the power. The pull force, the pull and push force over a meter, over 10 meters, depending over 10 meters. So this year, 5 newtons of force as a ratio of, and then that's just as a ratio. So 5. So K is when K equals when K equals 5. Get rid of when the force equals 50 in K. They in IK the force equals 10 because it doubles. So the 10 equals 10. So if the share, if they have 50. K is 10, but the priority of K, so K has inverse kilometer holds 5 more. So if the IK of 10 meters due to newtons of force, and there's 50, 10 over 50 is 5, and 50 over 10, 50 over 10, 50 over 5 is 10. Because these are basically the force of 10. So 50 over 5 is 50 divided by 5. 50 divided by 5, which is 10. So they have shared 10 liters. This should have 10 liters, but this is about force. So because because they shared 10. So 10 units, the IK has its own 10. The one for units is 10. When you pull down, when you have a pull, you have a push, and the push is basically because the object is at rest, and the object is really pushing back or something. So that's the idea. The object is pushing back you at rest. So that's net force equals 0. So the net force of the system working against you is 0 because it's pushing back at you, and that's why it's stationary. So in this kind of framework, that's the problem here of the stiffness. So the stiffness has an inverse kinematic that is net force equals to 0, and you can verify this by ensuring that the net force is 0 in a system of linear using this kind of force framework, which is what I'm trying to do. So IK equals IK of F of Ix, which is inverse X, is pushing back of F of I force. The net force of Ix or sub Ix of Ix is a parameter of I sub I of X, which is the inverse X, which is not. I'm busy. I'm busy. Come in. Sorry. Hello, doctor.
How are you doing?
I'm fine.
You've been in your bedroom all day?
Yeah, I've been busy. I've been working.
Okay.
Yeah.
I'm going to leave you to continue on your work.
Yeah, good. Thank you. So the Fix of the system of will be 0, because 0 is just nothingness. But because it doesn't matter what's pushing. So you go push, you go pull. Just remember that. But if you have to put additional force, you have to keep additional force to keep the object. So if you don't know, you have to keep adding additional force to keep the object moving in one direction, and that's what the problem is. The force has to be. It doesn't matter how much power you have to have the same power equivalent to it, which is called the potential energy. So you go to the of power. So I'm gonna go to the second one. So the formula will be net force of inverse force. Net force over inverse force 1 over x. Net force. So the net force of inverse force 1 over x, which is 1 over x, not x. 1 over x is equal to 0. Is equal to 0 when is equal to 0 when there's a if difference because if you go it's not because if it's stationary when there's no power when there's no power we got something that can't be moved to say so when you go push so you have to have double so you got the K which is stiff so when the stiffness K so you got equals 1 that equals to negative K. So I got here the force of negative K, the force of 1, net force of 1 over x equals negative x, negative K. So that's the first one I got. So the net force, which is the summation of the forces of 1 over K equals negative K, and the force, net force of x equals K, when K equals 0. So this is the first one I have. Right? So you get a net force of 1 over x equals K. K equals 0, and K is the stiffness of the system. So it is no stiffness. It is nothing. Okay. K equals 0, or K equals 0 or U. U is just representing of the unit system. So K equals I. So this is 1. U or I, K equals I, because if I use I, I'm using indexes. So because my one is I, not even U. So K equals the index I. K equals 0 or K equals U or I. So K can be so K is a vector of 0, U, I, and U. So K equals so K is a eigenvector. So let's call it K is an eigenvector. So K is either I 0 I and U. So again, so the net force, the total summation of forces 1 over x equals negative K, and K is either 0, 1, 0, which is nothing, I, which is the imaginary unit, I, and U, which is the unit of imaginary unit. So you get because I'm using I as indexing. I'm using I because I is imaginary. So because it's a computer program, so it's not just an indexing. Also, I is the imaginary unit, which is third, which is like negative 1, which is negative 1. So you get I there, which is I. So you get I. So you get I. You get I, J, or should I use I, J, K? Or I don't know. So I don't know. Actually, I don't think to do because I have to define this properly. So I don't get confused. So I'll use I. This is much use I, but use I as the index notation I, J, K. To symbolize the dimensions of U, V, W. So U, V, W. So if you go I, you go U. If you go J, you go V. If you go to K, you go W. Because these represent dimensions of indexing. So you get I, J, K. So this is the units of I. So you get the index of I, which is nothing. So I, U, which one can dimensions? So so the K matrix can be. So how goes that? So you get K, U, K, U, K. U, I, and u are 0, u are nothing, u nil, u 0. So this u, so u sub k is equal to u sub k, u sub I, u sub ijk, equals which is not equal to u sub 0. Which is not equal to ijk is not equal to k, is not equal to j, is not equal to v ijk, because the v ijk is not there. So you got to not there. So you got to not there. So that's how it works. So my round is about to ring. No. Oh, I thought it was finished. So and one more thing. So so we got a potential differential equation, which is this. So the first one's done. So we got this difference done. So we can reformulate ik and k. So now we got the potential equation. So we got potential energy. So we got potential energy, which is about to do work. Something that has potential to do work. Something that can act. So basically, this is an auxiliary construction in my framework. So it has potential to do work. It has potential to be seen. You can observe it. Or something. It has potential to fall. It doesn't want to. It has potential to drop. Because you have your height, and that energy is basically a system of height. So if all you just need to let it go. So the potential energy is a half of the k squared. So this is a half. So the potential. So if you have a spring and you put it down, the potential is half of the kx squared, k, which is the kinematics of k is the stiffness times x coordinate system, and then times x, which is squared. So k is the displacement on the sun. If kx is the displacement of the spring in neutrals, and if I have a spring and I let it go, I have to put a half of the energy in to let it go to slow. So that's really half. I don't have to push it. There's no push. So you have to pull the spring. I don't have to push the spring to activate it. I just have to let it go. So I let the spring go, and the spring. So this is correct. So so this is correct. So half of the x squared will be half of the x squared. So basically, because you got a half of the kinematic spring, you got the squared here. So you got to multiply by 2. If it's 1 divided by 2, you get x squared. If it's 1 divided by 3, you have to do 1/3 of the energy because you have put 3 times the spring down. So 1 over 3 will be k times x to the power of 3, and get PE equals the integral x over the integral p potential energy. So you get potential energy. You get the potential energy, the amount to do work, and you get the actual energy, which is the work done. So you get the work done, which is force times displacement equals work. But you got the potential energy, which is PE equals 1/2 of kx squared. So you get this formula here. You use it to verify the work done. So you just need the force to be double. So or triple. So you get how this formula works. So potential energy equals the 0, starting from 0 to the integration of x, which is the all of the s, which is f of u given du. So du is the derivative of u, and u is supposed to be a dummy variable for the formula of the integral of a non-existent. So du works in graphs. So this is not complete again. So the potential energy, 0 given x of the force u. The force u. So the force u represents a unit of a whole unit in a dimension. So u will be the whole unit of x, and this is the force given u will be the force of the unit system of the u over integration over the graph integration, which is the area under the curve. Over the so this is the area under the curve of x. X is an axis, and d is the derivative of that unit of that segment. So du is of the segments of x. So d is the derivative of the segment of x. du. So the force we need. So this is saying that we need a force u over the derivative of u. So this works on so katoa, so u y ka x and toa toa, which is so you got to have the cosine. So this is not good enough. So you get the special. So this will be p potential energy equals x or the integral of x from 0 fu where u is is where u is the cosine, the cosine cos. So you get u over the root cos of over the polar axis. So this would be cos of the du derivative of u. So the change of u. So this would be for my first one. This would be the force du equals the force of cosine u. Force of if it's kinematics, it would be force of cosine u, which is du, or d or cosine u. Which is the root of cosine u, which is so u equals cosine of u, because you get x over y, but you know this x over y error. So so you have to take the root of it. So you have to work on the axis of polar coordinates. So you get the kind of actually you get the kind of cosine. So if you take a cosine, you get a sine. So this would be a cosine. So du would be so you get the cosine, you get the sine. Sine. So that'd be so you get so you get times minus 1 from the power. Minus 1 from the power. This is from the power of the system. So if you have a cosine, you have to get the root of the axis, and that axis will be sine. So cosine will become sine u, and sine u will become minus 1 for the power and divide 1. So I'm saying. So it's basically meant to math. So this one will be the 0 integral x f of u dx will be d cosine equals to sine u times sine u times minus 1 from the power and times by the power times minus 1 from the power times by the power and minus 1 from the power times by the power. Minus 1 for the power and times by the power. So this would be times cosine sine u times cosine u. So this would be, because you know you go cosine times sine times sine. So sine would be whatever would be the end result of so you have to keep sine. So sine becomes sine u times cosine times sine. And then minus 1 from u, cosine from sine. So this cosine from sine, which would be cosine, which would be, so you get a cosecant of u, which is cosine from sine, and then you get the divided by sine minus 1, so divided by sine u, and this would be the integration of the force u over du. So we just force du. So I'm writing this down. So we got net force equals 1 over x equals negative k. Net force equals x over k, and we get which is called stiffness, where k equals UVW u sub ijk and ijk for all. How do you say for all? I'll just write the number for all x, y, z. And then we get the signs. We get this one. We get PE, which is supposed to PE equals a half times k s squared. We get PE equals integral of x over 0 f of u du, and we now get PE equals 1 over u 1 over p, where p equals the power, where p is the power, it's the power. 1 over e, okay, 1 over e, 1 is an exponent, so e is an exponent, k x e, so e, where e is an exponential, equals exponent, and then we get force. So we get this one, my one equals p e equals, because you know you get two types of information, x over integral of fu equals equals f equals cosecant u d root of cosecant u over sine of u. This is SOHCAHTOA, which is y, x, z, which on the line. So the goal of this is to have the next one, which is that, and then we get last one. Another video we'll do this. So we get force equals k x, and that means a negative force will be a negative k over x, and then we get force equals force kx, and we get so this means a negative force equals a force equals a negative x. So that's it. So you get this kind of formalization. So I'm going to take a picture of this and I'll upload it to my system. But this is done. Because you know the system has to be working polar. So I don't know lambda calculus. I know Laplace calculus. So it's still very hard for me to use lambda because you know you got beta rules. You got to kind of rules you got to apply in lambda for power. So that's called beta reduction. But basically beta reduction and alpha reduction. You know what I'm saying. But you know I know there's one. But basically you can't reduce all the systems to one system. You can either use beta or alpha. You know to one system. But you know you can't reduce everything to the same framework. So those are called the rules of the dimensions. I call it in the game. Kind of the dimension given to the framework I'm from, and the kind of a power work duality of force of work equals force times displacement. But the goal is to have one rule set that you can reduce the problem to, and ensure that you can continue solving more problems as you attempt to use polar axis problems to solve the system. Okay, thank you guys. Bye bye. I'm not over the video now. But this is how the NSIGII protocol works. So again, the NSIGII protocol is it works on it's a non-linear springs. So this is the first one. This is non-linear springs model of the problem. But we also got more problems. So you got non-linear springs, and you got kind of what I call Snail's law. So Snail's law verifier. So what is that? So we go here. So we get Snail's law. So we go here. So we get spring physics. So we get this one here, and we get reflection and Snail's law. So this is Snail's law video. So
in the last couple of videos, we talked about reflection, and that's just the idea of the light.
So this is a geek for geek Snail's law. But you know, I love geek for geek. But you know, this is reflection. So you get reflection, you get reflection. And you get reflection, and you get so basically NSIGII is the reflection protocol. So but you also reflection. So you get reflection. So you know you have to bounce off the system medium. So to via step. So you can get so basically the protocol provides reflection, which is actually called like Snail's reflection, which is v over sine of theta 2. But I didn't really sure about that. So Snail's law, S for Sarah, N for November, E for Echo, Alpha Lima is the next feature I'm trying to work on. But Snail's law is basically the refractive index that determines whether the system reflects or reflects. But you know, it's basically meant to have a mirror of reflection that determines the kind of refraction angle the system takes to descend through the medium, because you know via the 3.0. So basically, NSIGII has an echo chamber, and the echo chamber uses refraction to reflect the message via the trident pattern. So you can three messages. So the three messages are springs, and they bounce off each other. So the three messages bounce off each other, and they send them. It doesn't matter how you send it. It's more just to send the message than actually get the message back. Because you know they have to bounce off each other to the surface. So if you put it one way, it bounces more out one way, and the spring, the refraction index, which is Snail's law. Okay, thank you, Namdi.